This screencast is about periodicity, specifically focusing on the trend in first ionisation energies. First, we need to consider what is first ionisation energy. So here's the definition, it's quite long. It is the enthalpy change when one electron is removed from each atom in 1 mole of gaseous atoms to give 1 mole of gaseous unipositive ions. So let's unpick this a little bit because some of these terms you might not know. The first one is this idea of enthalpy change. And enthalpy change, we tend to a little bit in using our heads the shortcut of an energy change, but all that is a heat change at constant pressure. And that just means that we can compare values because we've controlled some of the factors that affect this energy change that you might kind of use as a shortcut in your head. So you've got 1 electron being removed from each atom in 1 mole of gaseous atoms. So it matters that these are gaseous atoms, especially if you're asked to write an equation for it, to give 1 mole of gaseous unipositive ions. So that just means +1 ions. So let's write it in equation because actually that's far simpler than this huge long definition. So let's just use an atom M representing any metal, and it's a gas, and it's going to form 1 mole of unipositive ions. So we're going to remove an electron. Remember that when we represent anything in an equation like this, there aren't any coefficients, so there's no ones in front of these, but essentially this gap kind of here means that there is 1 mole there. And we're not talking about 1 atom, we're talking about 1 mole. So first we need to think about this process of removing an electron from something and what factors might actually affect the magnitude, how big this first ionisation energy is. The first thing that you need to think of is that ionisation energy is endothermic. Those electrons have got an attraction for the nucleus, so therefore we're going to have to input energy in order to remove the electron from that attraction that it feels for the nucleus. The size of that, how much energy we have to put in, is related to a number of different factors. The first thing to think about is the nuclear charge. So that is essentially how many protons are in the nucleus, because the number of protons affects how strongly the electrons are being held. The interesting thing about this, though, is that the nuclear charge itself actually doesn't really matter, not the actual nuclear charge anyway. What we're going to start to consider is an idea of something called the effective nuclear charge. And that is, regardless of how many protons are in the nucleus, how much the electrons that are in the outer shell actually feel the effect of that nucleus. So this is why we call this effective nuclear charge. An effective nuclear charge is affected by 2 different things. The first one is the size of the atom, and the second one is the number of full electron, I'll use shells, but it's kind of sloppy language, but it's fine to think of them as full electron shells that are in there. So it goes without saying that the further away an electron is, the easier it is to remove. That's because it doesn't feel the full force of the nucleus because of the distance. So distance is an important factor in this idea of effective nuclear charge. And then the number of full electron shells actually results in something called shielding. So every time there is a full electron shell between the nucleus and the electron on the outside that you're trying to remove, you have to kind of think of these as having like a force field that's stopping the power of that nucleus from going past. And so this shielding, the more shielding you have, then the less the electron in the outer shell is held and the easier it is to remove. The second thing you have to consider is any specific factors related to the electron configuration itself. With this, you need to be confident in writing full electron configurations with S's and P's and D's, but primarily because we tend to consider the first few rows of the periodic table, the first few periods, then really only S's and P's, but you do need to be confident with these. So You should by now know that these are orbitals, and if we have an s orbital and then we have 3 p orbitals, each of these can have 2 electrons in them. So if we look at this case in particular, I haven't told you what period this belongs to, or what principal energy level, but here we have got an electron configuration where we've got 2 electrons in this s orbital. We've got 4 electrons in the p orbitals, so we've got 2 that are together, and we've got 2 that are singly occupied. As we move in the electron configuration out, that p orbital is going to be slightly further away than the s orbital in the same energy level. So we would expect that if we were removing an electron from a p orbital, it might be slightly easier to remove that than from an s orbital if it's in the same principal energy level, if it's a 1s, a 2s compared to a 2p. And then the other thing is to consider this idea of electrons being paired. When we pair up electrons, the electrons are tiny negative particles, so they're going to have some repulsion. You can see that I've drawn these with one arrow up and one arrow down, and that is to represent an idea called spin pairing, which actually minimises the repulsion, but it doesn't overcome it altogether. So a paired electron is easier to remove than an unpaired electron. We'll first look at trends in first ionisation energy down a group. This is the simplest bit to look at because there aren't really any electron configuration aspects that we have to consider, because elements in the same group will have the same valence electrons, so they will have the same number of electrons in the outer shell. So you can see here that I've got group 1, and you'll notice that in group 1 the valence shell is always an S, is an unpaired S electron. So we're always comparing the same thing here. So here we're going to try and remove this final electron from these S orbitals. And we need to consider the actual nuclear charge. So I've written down the side here the number of protons in the nucleus. So here you can see I've added the data for the first 2 elements in group 1, lithium and sodium. And you can see that as we're going down the group, we're getting a decrease. So let's consider about all the factors that we've already thought about, why that might be the case. So we have got more protons in the nucleus. So we might expect those electrons to be held more strongly when we get to sodium than for lithium, because we've got more protons, more positive charge holding that electron in. However, what we've also got is that sodium is larger. We've got a greater distance between the nucleus and the outer electron. We also have more shielding. When we've got the lithium, I'll just highlight this, we've only got this one full shell, to use a sloppy term. We've only got one full shell of electrons there shielding the effect of the nucleus. When we get to sodium, we've got the 1 and we've got the 2 principal energy level that are actually providing the shielding and preventing the actual power of those protons in the nucleus from reaching that outer electron. So the 2 reasons that we need to say here are that sodium is a large atom with a greater distance between the nucleus and the outer electron. There's more shielding from full electron shells, and therefore the outer electron is less strongly held for sodium than for lithium, and therefore less energy is needed to remove it. Before we go into greater detail on this, we'll first consider what the general trend in first ionisation energy is across a period. So compared to comparing the elements on the left-hand side compared to the elements further on in a period. So the thing you've got to remember as you go across the period is that the number of protons in the nucleus increases. The electrons being removed are in the same energy level. So that was shell when you were at GCSE. Because of this, the shielding is the same. We tend to say negligible change in shielding. We also have a smaller atomic radius as we go across, so the atoms get smaller. So we can say that as a general trend, the first ionisation energy increases generally across the period because the outer electron that's being removed is generally more strongly held because of the reasons we've got there. Now let's look in the trend in ionisation energy across a period. This is more complicated, and this is where the factors about the electron configuration really matter. So to study this, we will look at period 3, which goes from sodium through to argon. And you can see I've sketched a very rough graph here. The actual values themselves don't matter. The increases and the decreases do matter here. The key thing to remember when we're looking at trend in ionisation energies across a period is that these are all in the same energy level. So in this case, this is the 3 energy level. So these are going to be 3s and 3p electrons that are being removed. So therefore, there is no change in shielding. So we've just got the shielding from the n equals 1 and the n equals 2 energy level. And that's the same for all of the elements we're going to study. The first thing we're going to look at, as we go from sodium to magnesium, we get an increase in the first ionisation energy. So we need to consider why is this the case. So we've got more protons in the nucleus. They are going into the same principal energy level and the same orbital. So therefore we have got a greater attraction to the nucleus because we've got more protons. So therefore the outer electron, or one of the outer electrons for magnesium, is harder to remove than it is for sodium. The next interesting feature now is that we're going to look from magnesium through to aluminium, and we can see that we've got a decrease here. So let's consider why we've had this decrease. So if we consider just using the noble gas configuration, what the electron configurations for magnesium and aluminium are. So I've written these here. The top one is for magnesium and the one below it is for aluminium. So we can see here that for magnesium, our electron is in the s orbital, the 3s orbital, and for neon it is in the 3p orbital. So the 3p orbital is slightly further away. You might consider a slight increase in shielding, but not really here. I'll put that in brackets. because you have got a full orbital there. And so the electron, the 3p1, is less strongly held than the 3s2, the one that is in the 3s2 of the magnesium. So despite the fact that aluminium has got one more proton, the fact that the electron is in the 3p is overcoming that and making it slightly easier to remove. The next you can see is a little kind of chain of 3. So as we go from aluminium to silicon to phosphorus, we get a little chain of 3. I'm just going to annotate those with the outer electrons so that we can see where that comes from. So in each case here, what you've got is an increasing number of protons in the nucleus, and therefore, and we're all going into the 3p orbital, so therefore we've got no change in shielding, no change in distance. So therefore, each time we add a proton into the nucleus, then it gets harder to remove an outer electron. So that one's fairly simple. Our next one, where it gets a little bit more complicated, is you can see we've got a dip here. And we've got a dip here going down to consider an electron configuration which ends in 3p4. And this is the interesting part that we talked about a few slides ago, to do with the pairing of the electrons and the effect that has on how easy it is to remove these things. So we'll just annotate that one. So we have a decrease here. So the best way to consider this is to write your electrons in boxes configuration. So here, using the noble gas as a shortcut, I've got my electrons in boxes configuration for this elements. Here I've got phosphorus on the top here, so I've got 2 in the s orbital here, and then I've got 1 each in the 3 singly occupied p orbitals. And then for sulfur, I have got the 3s2, and then you can see that one of the p orbitals has got paired electrons in it, and then the other ones are singly occupied. Now this pairing means that the electron, the 3p4 electron configuration, it's easier to remove an electron from that because you've got paired electron and you've got repulsion. And then after that, the trend carries on much as we'd expect. We've got more protons in the nucleus, and we've ended up with it being much harder to remove it when we go through to argon. So let's just add those notes on here, and that is just there for completeness. So let's summarise our ideas about first ionisation energy. So the first key idea is that electrons are held in their orbitals by attraction to the nucleus. Therefore, if we want to remove an electron from an atom, then we're going to require an input of energy. Therefore, this process is always going to be endothermic. So that means that the enthalpy change is going to be positive. The size of this energy input depends on a number of factors. And really, when you are looking at comparing cases, the first thing that you should do is start thinking about the electron configuration and also the number of protons. Once you've considered that, then you can think about things like the size of the atom. Just how far away is that electron? The further away it is, then the easier it is to remove. Think about shielding. Full shells, to use a sloppy term, full shells of electrons stop the force of that nucleus being felt by the outer electrons. Think about the orbital that the electron's being removed from. So within the same energy level, it will be easier to remove from a P than it is from an S due to a little bit of additional size, a little bit of an additional distance from the nucleus. And then you've also got the idea of paired up electrons. Do you have to consider those? Because it's much easier to remove an electron that's in a pair than it is to remove a single electron. Overall, the idea of first ionisation energy is it actually really gives us a whole load of clues about the electron configuration of an atom. We can use values of first ionisation energy to predict trends when we can see a periodic table, and we can kind of work backwards. So there's lots of different questions that can be asked about this, but this gives you overall a summary of the ideas. So here are just a couple of exercises for you to practice what you've learned in this video. You'll notice, the keen ones amongst you, that I'm asking you about elements in period 2 here rather than in period 3, which is the one that we spent most of this video studying. The thing to remember is that this periodicity is related to electron configuration and proton number, so therefore anything that you observe in period 3 would also be observed in period 2 because they've got the same kind of shape to them. They've got both S and P electrons. So that means that you can use the ideas that we've done with period 3 with these exercises in period 2. So if you just pause the video and have a go at these and summarise them, and if you just check back in a moment, you'll be able to get a verbal summary of what your answers should cover. Okay, that's you checking back just to see what your answers might be on this. So question 1 is asking you to predict which would have a higher first ionisation energy, lithium or beryllium. So here you need to be making a comment about the outer electrons being in the same orbital. In this case, these are 2 s electrons that are being removed. So you need to say that you have got an increase in the number of protons in the nucleus. You have got a decrease in atomic radius because we see that going across the period, and that therefore the electron that is being removed for beryllium is harder to remove than the one for lithium. So you would expect beryllium to have the higher first ionisation energy. So we're making sure we are mentioning protons in the nucleus. For completeness, we're also mentioning shielding, so there is no increase in shielding because the electrons are in the same orbital, the 2s orbital, and the atomic radius is decreasing. So we're mentioning all of those things, and that means that the electron for beryllium is harder to remove than for lithium, and the value is higher. For question 2, you were just sketching a quick diagram to show what this would be like. So I'm just going to do, so you'd have 1, 2, 3 in a row with a dip in the middle and the other 3 going up like that. So you need to be able to explain the trend of 3s, and that trend of 3s is due to the same things we've just been talking about a minute ago. It's the increase in the number of protons in the nucleus, decrease in atomic radius, and the electrons being more strongly held because we haven't got any change in shielding, because these are p electrons that we're considering. And then the other important thing that you need to be looking at is this dip, so the dip in the middle. And here you're going to be talking about the fact that we are comparing a 2p3 here with a 2p4 there, so you need to be talking about pairing of electrons and repulsions there.